Section: Introduction. In this section, we discuss our approach to training xLAM, focusing on several key aspects of our data pipeline. We emphasize the importance of unifying and augmenting data to enhance diversity and reduce overfitting. Our preprocessing and augmentation methods significantly improve how well our agent models perform across different environments. We also highlight the role of scalable, high-quality data synthesis in boosting agent model performance. Our synthetic dataset has allowed xLAM models to achieve impressive rankings on the Berkeley function calling leaderboard, including the top position, with smaller models performing comparably to much larger ones. We evaluate the xLAM series against public agent benchmarks, showcasing their strong performance across various tasks. By open-sourcing these models, we aim to contribute to the development of open-source agent models and share valuable insights into effective data processing and synthesis techniques, addressing critical challenges in creating competitive alternatives to proprietary models. Section Summary. In this section, we highlight the advancements in autonomous agents driven by large language models, LLMs, and the challenges faced by the open-source community, particularly in data quality and diversity. We introduce xLAM, a series of open-sourced models designed to improve agent performance through effective data processing and synthesis techniques, aiming to bridge the gap with proprietary models. Section: Data Unification. In this section, we discuss data unification. We recognize that existing agent datasets come from various environments and formats, which introduces noise and complicates data augmentation and verification. Models like Nexus Raven, Gorilla Open Functions, and Agent Ohana have shown that a clear, universal format can greatly improve model performance. By standardizing data formats, we can reduce noise and make data augmentation and quality verification easier, leading to a more effective framework for training and evaluating models. A consistent format also simplifies model training and enhances the model's ability to generalize across different benchmarks. We design our unified data format in a function calling style, which is crucial for how models understand and perform tasks. Our unified format includes several components: task instruction, available tools, format instruction, few-shot examples, query, and steps. The available tools define what actions the agent can take, while the format instruction outlines how the agent should present its responses. Each step organizes the agent's output, the environment's feedback, and the user's follow-up input into a structured format. In purely conversational interactions, where no APIs are triggered, the related entry values remain empty. This unified format is adaptable to various environments and tasks, allowing our data processing pipeline to handle large datasets effectively. The modular design also supports detailed data augmentation and quality verification, which are vital for improving data quality. For data augmentation, we focus on enhancing data diversity by applying transformations to the existing dataset to create new, synthetic samples. The unification step simplifies the application of these techniques. We categorize our augmentation strategies into prompt format augmentation and instruction following augmentation. In prompt format augmentation, we create different prompt formats based on our unified data structure. This includes shuffling the order of available tools and their details to prevent model overfitting. We also concatenate different sections of the input using special tokens to form training prompts. For instruction following augmentation, we aim to diversify instructions to improve the model's ability to follow them. This involves rephrasing existing instructions and adding new ones while ensuring accuracy. We verify these new instructions to maintain consistency. We use two methods: rephrasing task instructions with large language models, LLMs, and preparing multiple output formats to prevent overfitting on a single format. To ensure data quality, we analyze the unified dataset to identify errors using both rule-based methods and LLMs. We look for undefined function calls, incorrect argument types, argument hallucination, and low-quality reasoning and planning. Undefined function calls occur when the model generates a function call not present in the provided list. We also check for incorrect argument types, where the model may generate the right value but in the wrong format. Argument hallucination happens when the model includes values not found in the user query or previous steps. We use LLMs to detect these mismatches effectively. Lastly, we filter out low-quality reasoning and planning by using heuristics and evaluating data trajectories with models, followed by human verification. Section Summary. In this section, we propose a unified data format to standardize diverse agent datasets, reducing noise and enhancing model performance through improved data augmentation and quality verification. Our approach includes modularized data organization, various augmentation techniques, and rigorous quality checks to address common errors like undefined function calls and argument hallucination, ultimately leading to more robust model training and evaluation. Section: Data Synthesis. In this section, we identify several limitations in publicly available datasets based on our findings. Firstly, these datasets tend to be static, created by weak models, limited in their scope, and, crucially, not verified through execution. Secondly, they primarily focus on a single function calling type, meaning they only generate one function call based on the provided tools. However, real-world situations often involve multiple requests, requiring the model to handle concurrent function calls in a single response. To tackle these issues, we employ a systematic data synthesis framework called API-Gen, which generates verifiable datasets from a collection of executable APIs. The core idea involves a multi-stage verification process to ensure the generated data's accuracy and quality. This includes format verification, execution verification, and semantic verification, which help us filter out low-quality data, such as those with hallucination problems or incorrect argument values. We utilize over 3,673 APIs from 21 categories in Toolbench to create a total of 60,000 high-quality samples, using strong open-source language models like DeepSeek V2 Chat and Mixtral-8 by 22B Inst. This framework significantly enhances the dataset's robustness and applicability by effectively identifying low-quality data. For supervised fine-tuning, SFT, our dataset merges training samples from three key sources: cleaned and augmented agent datasets, a synthetic function calling dataset, and general instruction tuning datasets. We integrate diverse instruction tuning datasets from Dialog Studio and Data Provenance to improve the general instruction capability of our xLAM models. We apply rule-based techniques to eliminate low-quality data, such as repetitive phrases and inappropriate content, and we deduplicate similar user queries while organizing the data by domain. We then prompt Mixtral-8 by 22B Instruct v0.1 and DeepSeek v2 to evaluate both the entire dialog and individual system responses, with this instruction data making up 20% to 30% of our training set. To boost the function calling ability of xLAM7 BFCR and xLAM1 BFCR, we use a targeted training approach, sourcing 50% of their training data from our high-quality synthetic function calling dataset and the other 50% from various tasks within our training set. For direct preference optimization, DPO, we prompt less powerful models to generate and rate responses from each source, sampling a subset for human verification. After refining the models and prompts, we classify some responses as rejected samples. In our modeling approach, we utilize supervised fine-tuning, SFT, and align model checkpoints with the DPO method, benefiting from our flexible data pipeline. Our training code is based on Hugging Face transformers, Accelerate libraries, and PyTorch FSDP. During training, we conduct multiple epochs with randomly shuffled datasets. When employing data parallelism across devices, we diversify random seeds based on process IDs to ensure balanced data distribution, enhancing the robustness and reproducibility of our training. We fine-tune general xLAM models on NVIDIA H100 GPUs, using a full fine-tuning framework with a fully sharded data parallel algorithm. For xLAM-8 by 22BR, we incorporate LoRa to maintain the model's original capabilities and prevent catastrophic forgetting, which is also applied for DPO alignment across all xLAM models. Additionally, we implement a cosine learning rate scheduler with 100 warm-up steps to optimize performance. The xLAM FC models are designed for various function calling categories, including simple, multiple, parallel, and parallel multiple queries, enhancing performance in different scenarios. For example, a simple query like asking for the weather can be handled by calling a specific function, while multiple queries involve selecting the right function from several APIs, and parallel queries require executing multiple function calls at once. We also train the models in relevance detection to ensure alignment between function calls, execution results, and query objectives. Section Summary. In this section, we identify limitations in existing datasets, such as their static nature, and focus on single function calls, and propose a systematic data synthesis framework called API Gen to generate high-quality, verifiable datasets using a multi-stage verification process. We also describe our approach to supervised fine-tuning, which combines diverse training samples and employs techniques to enhance model robustness and function calling capabilities across various scenarios. Section: xLAM Model Series. In this section, we introduce a series of agent models designed for various applications, with our main model series, xLAM, based on the Mixtral and Struct models. Our goal is to provide balanced performance across a wide range of tasks, from complex interactions to function calling applications. To achieve this versatility, we train xLAM on uniformly sampled data from our training dataset. Alongside the general xLAM models, we create two specialized models for function calling tasks, xLAM 7 BFCR and xLAM 1 BFCR, which are based on DeepSeek Coder 7b Instruct v1.5 and DeepSeek Coder 1.3b Instruct, respectively. The smaller models are more accessible, allowing users to host them on a single GPU for various function calling tasks, from simple queries to handling multiple requests simultaneously. By offering models of different sizes and specializations, the xLAM series meets diverse user needs and computational capabilities, making powerful agent functions more accessible for real-world applications. We evaluate our model's performance across 4 rigorous benchmarks: WebShop, ToolQuery, ToolBench, and the Berkeley Function Calling Benchmark. Each benchmark assesses different aspects of model capabilities under various conditions. WebShop simulates an online shopping experience with around 250 test cases, testing an agent's ability to assist in e-commerce tasks. ToolQuery evaluates an agent's skills in using tools for information retrieval across 3 settings: weather, movie, and academia, with 60 test cases in total. We use testing configurations from Agent Board for both WebShop and ToolQuery, focusing on success rate and progress rate, with success rate being the more critical metric. ToolQuery Unified is a variation of ToolQuery that requires agents to follow a specific format for task instructions and tools. This setting helps us evaluate agents' reasoning and tool usabilities in structured formats. ToolBench allows for real-time evaluation of multi-turn reasoning and interactive capabilities, featuring around 1,000 test cases and using pass rate as the evaluation metric. The Berkeley Function Calling Leaderboard Benchmark provides a comprehensive framework for assessing an agent's ability to reason about and execute function calls in various programming languages. This benchmark includes over 2,200 test cases, challenging models with complex scenarios like parallel function calls in languages such as Java, JavaScript, and Python. We measure performance using metrics like abstract syntax tree accuracy for non-executable queries and executable accuracy by running APIs. We utilize the latest BFCLv2 version, which includes live function calls and real-world scenarios contributed by users. This version addresses issues like data contamination and bias, reflecting real-world distributions more accurately. Notably, our models were trained before the release of this live data. In the WebShop environment, our xLAM 7BR model achieves the highest success rate of 0.414, outperforming other general language models and specialized agent models, demonstrating its effectiveness in web interactions. In the more complex tool query environment, xLAM 8x7BR and xLAM 8x22BR rank second with a success rate of 0.683, showing significant improvement over baseline models. When we present the tool query system prompt in a unified format, we find that xLAM models perform more consistently than GPT models. Our best xLAM model maintains strong performance, attributed to its training on trajectories that follow the unified format. This consistency contrasts with the observed decline in performance of other models when constrained to specific output formats, indicating a drop in their reasoning abilities. Section Summary. In this section, we introduce the xLAM model series, designed for various agent tasks, including specialized models for function calling applications, ensuring accessibility and adaptability for users with different computational resources. We also evaluate the model's performance across multiple benchmarks, demonstrating their superior capabilities in environments like WebShop and Tool Query, particularly in comparison to other state-of-the-art models. Section: Toolbench. In this section, we present the results from Toolbench, where our xLAM models show strong performance. They outperform both Llama v2 and GPT 3.5 Turbo 0125 in all test scenarios. Additionally, xLAM models excel compared to Agent Ohana 8x7B when faced with new instructions and tools, and they perform similarly to GPT 40125 Preview in situations with unseen tools. These findings demonstrate the xLAM model's strong abilities in multi-turn reasoning and complex tool usage, effectively managing both familiar and unfamiliar tasks. We also conducted an ablation study on the 7B models to assess the effects of different steps in our data pipeline. For this analysis, we prepared 3 datasets: raw data, augmented data, and augmented plus clean data. The raw data is the dataset before we unified the data, while the other 2 are after unification. The evaluation results from models trained on these datasets show that augmented data consistently performs better than raw data across all metrics, with improvements of 2.3% on Toolbench, 5.8% on WebShop, and 18.3% on Tool Query. Moreover, adding data cleaning significantly boosts performance on Tool Query, yielding an additional improvement of 23.4%. These results underscore the effectiveness of our data augmentation and cleaning processes.